Okay, so we're going to talk about further applications of Newton's laws, which will deal mostly with friction. There are other things, drag and elasticity, that I think we'll set aside because that's a bit more than we need to get into for this course. So, total hip replacement surgery, common procedure. The head or ball of the patient's femur fits into a cup that is a hard plastic inner lining, and friction is a key concern here, right? And that's where the damage came in the first place, is friction, and maybe more friction than even was predicted, because cartilage wore out, and once the cartilage is gone, you have more friction going on, and that causes a lot of damage. And so now you do a replacement, and you want to have a situation where you're not going to continue with that damage happening. When we talk about motion, free fall motion, we say we're going to do this in the absence of air resistance. That would be drag. We'll talk about that just a tiny bit. But in x-axis, if we have an object sliding across another surface, you're shoving a box across the floor, there is friction. No matter how smooth the surface of the box looks or how smooth the floor looks, if you look at it at a microscopic level, you'll see that they're both really rather bumpy, and when you force one thing to slide across the other, there's friction. If you just look at the surface of your hands look moderately smooth, but if you rub them back and forth across each other, eventually you feel heat, you feel this abrasion, and this thing is friction. There's a frictional force going on, and we're losing energy by rubbing our hands back and forth across each other, because that friction is generating heat and other things that are energy that's then being lost to the surrounding environment. So in order to deal with things like friction, we need another tool. Previously, we've had this fun where I said, hey, draw a picture of what's going on, and that will help you think about the problem. And that is entirely true. But now that picture that we draw is actually a tool that we'll be using in our calculations. So the physical picture here is a disembodied hand holding a textbook up in the air. But the tool that we're going to use is called a free body diagram. And a free body diagram is where we draw an image of the force acting on the textbook in the positive y-axis, and the weight of the book depicted in the negative y-axis. And in this case, they're equal and opposite to each other. So we have a vector going up in the positive y-axis and a vector going down in the negative y-axis. And if the book isn't moving, then the net force on the book is 0, meaning that the upward acting force is equal to the downward acting force. And we have a free body diagram. Another situation is, say you're trying to move a large chair across the floor. If you push the chair purely horizontally, that would be one situation. But in this case, the force isn't purely horizontal. Part of the force is directed down in the negative y-axis, and part of the force is forward in the positive x-axis. Well, in this case, the normal force, that's the force that comes out of the floor acting on the chair in the positive y-axis, is equal to the combined forces of the weight going down as well as the component, the y-axis component of the person's push. So negative F sine theta is this person's push, because part of it's directed down, and then the weight, those are both negative forces, and the normal force has to be equal to the combined two of those. That's going to be important to us because friction is proportional to the normal force. So we'll have to be able to know how big the normal force is. So the origin of friction, like I said, the microscopic bumps on the road there. There's two kinds of friction. There's static friction. When you push on something, maybe you're sitting at a table now and you push on the table just gently and the table's not moving. Well, you're providing a push in the positive x-axis. The table, or friction from the table interacting with the floor, is pushing in the negative x-axis, equal and opposite to your push. That is a static frictional force. Now you can keep pushing harder and harder and harder, and eventually you'll achieve the maximum static frictional force. That's the force that it takes just to get it to start moving. And it's the coefficient. So this little u thing is a Greek letter mu. And it's mu sub s is a static frictional coefficient. We'll look at a table of these values approximately, times the normal force. So the normal force is the weight, equal and opposite to the weight of the table. That's a force that's acting up, and then times the coefficient of static friction gives us the maximum static frictional force. That's how hard you have to push in order to get it to just start moving. The other thing is kinetic friction. Kinetic friction is the coefficient of kinetic friction times the normal force. Coefficient of kinetic friction then is a value that we'd look up on a table, but if you're just sliding a box across the floor, you slide it across the floor and it pushes back while you're pushing on it. And if you stopped pushing, it would slow down and stop, or just stop immediately if you're not moving it very fast. So it's static frictional force and kinetic frictional force are the two values there. So we have a spring scale in our lab kits. We could try this as we pull on something to get it to just start moving, and then keep pulling on it and see what happens when it is sliding. It's kind of hard to read that value, but it's something we can do. Consider a horse pulling a buggy. Is the following statement true? The weight of the horse and the normal force exerted by the ground on the horse constitute an interaction pair that are always equal and opposite according to Newton's third law. So remember Newton's laws. It's not that. It's not an interaction pair because the normal force and the weight aren't the two things that are acting on each other. This is really, really picky stuff, but there's an upward acting normal force between the ground on the horse and the horse on the ground, and then there's a downward acting normal force. So upward acting and downward acting normal forces, but the origin of the force on the horse is the Earth's gravity pulling on it. It's really picky stuff. Don't worry about it. Okay. No, I don't think we need to worry about interaction pairs. We want to get to this. So typical coefficients of friction. Rubber on concrete, when it's nice and dry out, would be a case where the coefficient of kinetic friction is 0.8 and the coefficient of static friction is 0.9. Whereas rubber on wet concrete drops down considerably. I don't know if you've spent any time thinking about this. Winters in New England will make many of us think about this, but we need friction in order to drive our cars, right? So these are pretty high coefficients of friction. Rubber on concrete, this would be the wheels of our car on the road. We want friction. We need friction in order to move. When your car is sitting there at rest and you put it into gear and you step on the accelerator, what makes you move forward is friction between your wheels and the road. And in the winter time, when our driveways are sheets of ice and we've tried to shovel the best we can, but it's still icy coated everywhere, we step on the accelerator and our tires just spin around because we don't have good traction. If you're driving down the road and you turn the wheel to the left, you would hope that your car would turn to the left. But if you're on a sheet of ice, you turn the wheel to the left and you keep going straight. You need that friction in order to drive around. So there's times when friction's great and important, and then there's times when you'd rather eliminate friction to have an engine work efficiently or something. So here's some different coefficients of friction. Person has a choice of either pushing or pulling a sled at constant velocity, as the drawing illustrates. Friction is present in this case. If the angle theta is the same for both cases, does it require less force to push or to pull? Well, what might be more comfortable for you is to push, because you can kind of lean into it. But in terms of the actual force required, in this case, this person is pushing and part of their push is down. It's increasing the normal force between the sled and the snow, and there is some friction. It might not be much, but there's some friction, in which case this would require more force to get it to slide forward in this case. Whereas here, if you're pulling on the rope, part of your force is lifting up the sled. That's decreasing the normal force. Therefore, the friction involved would be less because there's less of a normal force. Okay, this is a classic kind of homework problem. So when you push a 1.8 kilogram book resting on a tabletop, it takes 2.25 newtons to start the book sliding. Once it is sliding, it only takes 1.5 newtons to keep the book moving with constant speed. What are the coefficients of static and kinetic friction between the book and the tabletop? So we said that static friction is the coefficient of static friction times the normal force. Well, the normal force is 9.8 times the 1.8 times the mass. The normal force is mg, the weight of the book. And then the force, the static frictional force, in order to get it to just start sliding, is 2.25 newtons. So 2.25 newtons equals coefficient of friction times the normal force. So coefficient of friction is going to equal 2.25 newtons divided by, in parentheses, 1.8 times 9.8. And we'd figure out that we have a very small coefficient of static friction here for this book. Likewise, we'd find out that we have an even smaller coefficient of kinetic friction. If you notice from our chart here, the coefficient of kinetic friction is almost always smaller than the coefficient of static friction. I'd say it's always smaller, but it's equal right here for Teflon on Teflon, but that's kind of a bizarre instance. But everywhere else, once you get something sliding, once you break that force of static friction, you jump into a case where kinetic friction is smaller and it's easier to keep it moving. This is like the chair example from the very first image of a free body diagram. So if you're going to move this large crate and you're going to push down at an angle of 21 degrees, then we have to figure out that the normal force here is going to be F sine 21 degrees plus 32 times 9.8. So we figure out the normal force. We're given, and we don't know the force, so we're going to have to find that eventually. We have the coefficient of static friction here, 0.57. And so we figure out the x-axis component, F cosine 21 degrees equals 0.57 times F sine 21 degrees plus 32 times 9.8, and we're then able to solve for F. We have F on both sides of the equation. Kind of a hard problem, but it's one we could figure out. Okay, you're pushing a wooden crate across the floor at constant speed. You decide to turn the crate on end, reducing by half the surface area in contact with the floor. In this new orientation, to push the same crate across the same floor with the same speed, the force you must apply is about 4 times as great, twice as great, equally great, half as great, or 1/4 as great. Well, it turns out, if you look at the equations for friction, coefficient of friction times the normal force is equal and opposite to the weight. Nowhere in there is surface area part of this equation. So if this crate is made of wood the whole way around, it doesn't matter what the surface area is. If it has the same mass, it's going to have the same frictional force. So the force we apply would be the same. All right. Oh, this one's hard. If you have something sliding down an incline, inclined planes are a tricky thing. Because on an inclined plane, if you have something that's purely horizontal, then the normal force is equal and opposite to the weight, and there's nothing that would compel it to move horizontally except some sort of external force. Here, on an incline, you can imagine you go down to the park and you slide down the slide. Well, part of your weight is pushing you down toward the surface of the earth, and that can take you down the inclined plane. It's compelling you to move down toward the surface of the earth, but you're not falling in free fall. It's only some portion of your weight. So it turns out that on an inclined plane, the component of your weight, mg, that makes you slide down the incline is mg sine theta, and it turns out that the normal force, which would then be responsible for friction, is going to be mg cosine theta, another proportion of your weight. So angle theta is the angle that the inclined plane is inclined at. So we have mg sine theta as the force that compels you to go down the inclined plane. And then mg cosine theta is the normal force, and coefficient of friction times mg cosine theta would be the kinetic frictional force. So you're able to figure out the net force on the incline, how much force is pulling you down versus how much force is holding you back, and you could figure out what's going on there. So if an object is held in place by friction on an inclined plane and you lift up one end of the inclined plane until it starts to slide, well, if you then keep it at that angle, as you lift it up, it's static friction holding it in place, lift it up, static friction holding it in place, and then finally it starts to move. Once it starts to move, it jumps from static friction to kinetic friction. Remember, kinetic friction is always smaller than static friction. So once it starts to move, if we keep it at that same angle, it started to move because we achieved the maximum static frictional force, but right then we jump to kinetic friction. So there's going to be a bigger force going down than there is holding it back up, and it should speed up as it goes down the incline once we've achieved that maximum static frictional force. All right, we can skip that one. Tension force is just a way of transmitting force from one axis to another. So tension in a string, if you pull on a string, the string pulls on the object. Well, if we align that up with pulleys, then we can take a force, gravity, pulling down on this mass in the negative y-axis, and by arranging these pulleys just so, get a force that's actually in the positive x-axis. We've changed the direction of the force by way of pulleys using this idea of tension in the string. So long as the string doesn't break, it's going to pull with a certain amount of force, and that pull is the tension force in the string. Can skip those, and just talk about the different kinds of forces. So there's gravitational force. That's the acceleration due to gravity acting on our weight. There's tension force. There's normal force, we've talked about that. There's frictional forces, and then there's centripetal force. That's going to go into another chapter, not something we have to talk about here, but centripetal force you've probably heard of. So that's another kind of force that would be involved in things. All right, that's enough for now.